Hello, this is Jack Jackson. I've got an interesting problem I want to look at from Euclidean geometry and involves some basics things that we study in geometry, but actually has something that might be a surprise to you. So what we're going to be talking about here is congruent triangles. Now let's remember our definition. We say triangle ABC is congruent to triangle DEF if and only if all the corresponding parts of the congruent triangles are congruent. So side AB has to be congruent to side DE, side BC has to be congruent to side EF, side CA has to be congruent to side FD, angle A has to be congruent to angle D, angle B has to be congruent to angle E, and angle C has to be congruent to angle F. And the order you write this does make a difference. And so you can see a couple of a pair of congruent triangles over here illustrated. We should be pretty familiar with this concept now. In fact, we spent uh, several weeks on this in my geometry course. You spent a lot of time on this in a high school geometry course. If you've been watching my videos through the playlist in order, we spent weeks talking about congruent triangles. In Euclidean geometry, here's one of the big questions that we wanted to ask. Can we conclude that two triangles are congruent with less than the defining six corresponding congruent measures known? And what is the minimum number of congruent measures we need to guarantee congruence? Okay, this is one of our main questions that we study in a good high school geometry course or college geometry course, and we studied it in my class quite a bit already, and we should know the answer. The answer is yes. We can conclude the two triangles are congruent with knowing less than the six corresponding congruent measures, and the minimum number of congruent measures we needed to guarantee congruence was 3, if they're the right combination of the corresponding congruent parts. So if you had side, angle, side, 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 angle, side, angle, or angle, angle, side, those turn out to be enough to make the triangles congruent, enough to get the other three corresponding parts congruent for free. But if we had side, side, angle, or angle, 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 those three corresponding parts congruent, that was not necessarily enough to make them congruent, although the AAA condition was enough to guarantee that the two triangles are similar. That's going to be important in a minute. So here are two questions for you. In Euclidean geometry, what if we have two triangles with four pairs of corresponding congruent measures from the three sides and angles? Are, are the triangles necessarily congruent? And the answer is yes, right? Anytime we get three sides and angles that are corresponding and congruent, that puts us back in one of those situations. We're either going to have one of, side, angle, side, angle, or so forth. That's going to work. So obviously we should know the next question, right? In Euclidean geometry, if there are two triangles with five pair of congruent measures from those three sides and angles, are the angles necessarily congruent? And of course the answer is no. Yeah, the answer is no. Well, how can the first one have an answer of yes with four pairs, and the second one is a no with five pairs? So what's going on here? Well, if you look carefully at this second question and the first question, there's a word I left out in the second question that was in the first one, and it's this word corresponding. That corresponding turns out to make a big difference. Okay, so this is how it turns out. If you get three sides and two angles that are congruent, uh, that's going to force the other angle to be congruent, and it is going to force the triangles to be congruent. And the only way that can happen is if they actually turn out to be corresponding, right? But there is a way, which we're going to see here, to take two sides and 3 angles and have pairs between the 2 triangles that are pair up and are congruent measures, but the other side is not congruent. But notice they will not be corresponding. Okay, so let's take a look at this in more detail. So again, if in Euclidean geometry, if there are 2 triangles with 3 pairs of congruent angles and 2 pairs of congruent so again, if we have 2 triangles with 3 pairs of congruent angles and 2 pairs of congruent sides, do the triangles have to be congruent? And if not, and I've claimed it's not, what additional restrictions, if any, must be placed on the lengths of the sides and the sizes of the angles to make this happen? So let's see if we can investigate this a little bit more in depth. So here's some things that turns out you're going to have. An angle of one triangle is congruent to some angle of the second triangle, and this is going to happen for all 3 different pairs of angles. Similarly, you have 2 pairs of sides from the 2 triangles. One side from one triangle and the other side from the other triangle have to be congruent, and this has to happen for a second pair, one from each triangle. So you've got a total of 5 congruent pairs of measurements. But notice we're not saying that these must be corresponding measurements. That's going to be the trick here. So let the vertices of the first triangle be A, B, and C. And let the second triangle, let's label them A prime, B prime, and C prime for the vertices, such that angle A is congruent to angle A prime is congruent to angle A, angle B is congruent to angle B prime, and then of course this is going to make angle C congruent to C prime. So even if we were just given those, that's what we were given. We weren't given something about, well, we were given the other angle. That's the third, one of 3 of our 5 things. So that's going to be congruent as well. But even if we were only given 2, we would still have to get that third one congruent. Now, when you've only got 3 things, you can always arrange them in such a way that they're going to correspond. So what we have is 3 corresponding pairs of congruent angles. That is enough to invoke the hypothesis of the angle-triangle similarity theorem, which says then that triangle ABC has to be similar to triangle A prime, B prime, C prime. Remember, what is similarity? Similarity means all the corresponding angles are congruent and sides are proportional. We'll get back to that in a minute. But notice I've said that these corresponding, once I get the 3 pairs of angles that are congruent, I said they have to be 3 corresponding pairs. That works for a triangle, but that's not necessarily true if it's got polygons with more than 3 sides. So for a quadrilateral, here's 2 quadrilaterals that have 4 pairs of matching congruent sides. A, say, matches F, B matches G, okay, or those all 4 are right angles in this particular case. D and F match and C and H match, and the matching colors here are congruent. But there's no way to match these up in a correspondence where the corresponding things. So if you go A to B to C to D, these 2 right angles are consecutive and these 2 are opposite where the right angles are. So these are not corresponding congruent angles, even though they do have 4 pairs. But there's no way you can do that with 3 because there's only, once you match one up, then you're going to be able to go around the triangle either clockwise or counterclockwise to get the next pair to match up, and then you're going to get the next pair to match up. There's only one left. So that's something special about triangles to get this to happen. Now, let's keep going with this. So far, what do we have? We have all the corresponding angles are congruent. Well, that makes them similar. So let's let the sides of the original triangle ABC be little a, little b, little c, labeled like this. Little a is the distance from B to C. Little b is the distance from A to C, and lowercase c is the distance from A to B. Okay. Now the corresponding links over here could be called A prime, B prime, and C prime. Now, since it's similar, we know there is some positive constant alpha so that A prime is alpha times A, B prime is alpha times B, and C prime is alpha times C. And we might as well put these things in order where A is less than B is less than C, or less than or equal to. There's some order. Let's just say that's the order. And we can also, one of these is bigger than the other triangle, similar, because we're claiming they're not congruent. Let's let the bigger one be the prime one. So let's let alpha be bigger than 1, greater than or equal to 1. If it's equal to 1, of course, we've got congruence. And then, but we're claiming that we might not have a congruence. Okay, so we're going to hope for an alpha. We're going to be able to find an example of an alpha that's bigger than 1. Okay, so of course, again, if alpha is 1, we got congruent triangles. So look at this. So for this to happen, here's what we want to have happen. We want to take the middle side here in the first triangle and let it match up with the smallest side in the bigger triangle. The biggest side in the smaller triangle is going to match up with the middle side, and then your big side of the big triangle and the little side of the little triangle are going to be different lengths, and that's what we got to set up. So if you look at this, I've got some circles. I kind of gave them. I put A at C prime just to help us see this, and so notice that B prime B is equal to A prime, or A prime is equal to B. See, they're both radius of that radii of that circle there for these line segments. And then these are both length C here. For this is length C, so B prime is C. Okay. So now what do we have? We've got some equations here. We've got A prime is B, but B is also alpha A. B prime is C, which is also alpha B, but wait a minute, B was alpha A, so C has to be alpha square A. And then C prime, then because it's alpha C, has to be alpha cubed A. So we have some relationships here among the sides of this bigger triangle. So let's summarize what we have so far. We've got A prime is alpha A, B prime is alpha square A, C prime is alpha cubed A. We've got A plus B is greater than C, A prime plus B prime. And we've got alpha, so that means alpha A plus alpha square A is greater than alpha cubed A. And then we've got alpha square minus alpha minus 1 equals is less than 0. Okay, so to see that, we've got A all the way across here, so we're just going to replace the A. So anyway, uh, the A prime plus B prime greater than C prime is just from the triangle inequality. So you've got this triangle here. The length of any side has to be strictly greater than adding the other two sides together. So we know that we've got A prime plus B prime has to be strictly greater than C prime. Now A prime, this is just substituting in. A prime is alpha A, B prime is alpha square A, and C prime is alpha cubed A. But now they all have an A, so let's divide everything by A, and we got alpha plus alpha square is greater than alpha cubed. Subtract alpha and alpha square from both sides. That gives us 0 here is greater than alpha cubed minus alpha square minus alpha, and then divide everything by alpha. The powers all go down 1, and now we got alpha. This gives us this equation. Okay, so we got us a nice little equation here. Okay. Well, what's the boundary? Okay. The boundary is our limit condition where it doesn't quite get there. Okay. Is if you put this equal to 0, that's the boundary. So it has to be less than that. So let's look at that equation. So if we solve for the boundary, we plug this in and we solve this. So what do we have? Well, we got to use the quadratic formula, right? So it's the opposite of b, so that's the opposite of -1, plus or minus the square root of b squared, -1 squared, minus 4 times a is 1, times c, -1, over twice a is 1. All right, there we've got it. 1 squared is 1. -4 times 1 times -1 is +4, plus the 1 is 5. And these negatives cancel. And so you get 1 plus or minus square root of 5 over 2. So that tells us that, and since this has to be less than 0, we have to be between these two values, between 1 minus the square root of 5 over 2 and 1 plus the square root of 5 over 2. But remember, we also said alpha was bigger than 1. So we're between 1 and 1 plus the square root of 5 over 2. But this particular number, 1 plus the square root of 5 over 2, is a very interesting number in mathematics. It has a symbol that we use for it. This is called phi. And this is also called the golden ratio. And here it is popping up out of this weird problem as an upper limit for what's going on here. This ratio, it never can actually reach pi. Out phi, never can reach it, but it is it's an upper bound, least upper bound for what alpha could be. And this is kind of remarkable because golden ratio shows up in all kinds of weird places. It shows up in art, shows up in nature, shows up in several different things in mathematics. So if we summarize all this together, here's what we ended up with. Triangle 1 has sides A, B, and C. B is alpha times A. C is alpha times B. A prime is alpha times A, the same as B. B prime is alpha times B, the same as C, which is also alpha squared times A. C prime is alpha times C, and so that's alpha cubed times A, and alpha has to be in the open interval from 1 to phi, phi being 1 plus the square root of 5 over 2. Isn't that kind of amazing? Now, let's look at this just a little bit more. What about, that's telling us about the angles. What about the sides? Well, just use law of cosines to solve for the sides, and here are the details worked out. Uh, Details worked out for that using the law of cosines. I'll leave that as an exercise to verify that I've got the right things there. Now, here is an interactive GeoGebra activity that I have that shows these things dynamically, where you can change this. You can change the size of the smaller triangle here on the left, the ABC. The A prime, B prime, C prime is over here. So you can basically move B and C anywhere you want them. And you can kind of see the circles there that I used to construct this. And then the value here, this goes from 1 to just shy of phi. Phi is about 1.618034. So I've got this that'll run from 1 to 1.6. If you get down to 1, they're actually congruent, of course. But anything a bit above 1 up to, but just below phi, they will work. So they're almost a ratio of phi here, but not quite. And so we have that. You can see the numbers kind of worked out here for the sides. Here I use K instead of alpha, and here are the lengths of the sides worked out. So basically, if you set a length for B to C, a length of A, like for example, if I want to set that at, let's see if I can set it to be 5. I don't know if I can get it exactly at 5 or not. Okay, if I had constructed this a little bit differently, I could set it wherever I want it to be, but I can't get it. Well, there's 4. I got it to be 4 exactly. Let's use that. So it's 4, and then I could let this be 1.5, for example. And this is an input box. 1.5 is in that interval. So that makes this B, if this is 4, B is 1.5 times that, so that's 6. And then 1.5 times the 6 is the 9. And then this one over here is also the 6 and the 9. and this one, uh, and this here is for the last side here is 1.5. Uh, let's see, it's actually, yeah, it should be 1.5 times the 9, should be 13.5. Okay. And then I'm not sure why it's saying 0.51. It should be just exactly 13.5 if that's exactly 1.5. But in any event, then what about the angles? Well, that's where these arc cosines come in to find the different angles. Here I have them measured in degrees, and so we just work out the law of cosines there to find the angles. And here you can see what they measure out to be, and they're all the same, right? See A and A prime are corresponding, they're the same. They're about 20.74 degrees, which measures with this, and it works out with the formula here. 32.09 degrees, that's for B here and B prime here. And of course that means C will have whatever's left over out of 180 degrees, 127.17 degrees for C and C prime. Okay, and you can just play around with this a little bit. If you go to this thing, I don't know if you can read that right there, but there's the link to it, and you can experiment with this and see what kind of different things. So I think this is really cool. Uh, cool problem. It's a good application of similar triangles, actually, not congruent triangles, but similar triangles. But it also informs us quite a bit more about congruent triangles and shows us that, hey, it's not this word corresponding is very important when we're talking about things like side angle side or angle side and so forth. Not only does the order of those things make a difference, the fact that the parts are corresponding when you match those things up makes a big difference. So I hope you found that interesting.